Now, I am going to discuss how to determine the inertia tensor for the robotic link having circular cross section. The length of the robotic link is assumed to be equal to L, and it is having the circular cross section with radius r. Now, here I am just going to consider a small element, the same element I am just going to redraw here. So, this is x, y and z. So, the coordinate system is attached here. Now, let us try to concentrate on this small element. Now, this is r, this particular included angle is your d theta. So, this arc is nothing but your r d theta. So, this is nothing but is your r d theta, and this is dr. So, the cross sectional area of this part is shaded part is nothing but is your r d theta multiplied by dr. And so, to determine the volume, that is your dV. So, what we do is, so this area r d theta dr multiplied by dx. So, this is nothing but the volume. So, if I want to find out the differential mass, that is dm, is nothing but rho dV, and that is nothing but is your rho r, then comes your d theta dr dx. So, this is nothing but the differential mass of this small element. So, the differential mass of this small element is nothing but rho r d theta dr dx. And now, let us try to find out its moment of inertia. And before that, let me write down that this particular z, z is nothing but, so this is r, this is theta. So, z is r cos theta, and your y is nothing but r sin theta. Now, using this particular expression, now we can find out the moment of inertia. Now, this your differential mass, as I told, rho dV, that is rho r d theta dr dx, where rho is the density. Now, moment of inertia about x x, that is I x x is nothing but volume integration y square plus z square dm. Now, y square plus z square is nothing but your y square plus z square is nothing but y square plus z square is nothing but r square sin square theta plus r square cos square theta. So, this is nothing but your r square. So, this is nothing but r square. So, y square plus z square is nothing but r square, and this particular dm is nothing but rho, then comes here r d theta dr dx, and let us try to find out the limit of this integration. Now, d theta, so theta will vary from 0 to 2 pi, then comes here r, r will vary from 0 to r, and x will vary from minus L to 0. Now, let us try to see what happens, like how to decide the range for this particular x. Now, here we have got the origin of the coordinate system. So, it is from minus L to 0, that is the range for your x. Now, if this is the range for x, so we can find out this and we can carry out this integration, and if we carry out this integration, we will be getting half m r square, where m is nothing but the mass of this particular the link having circular cross section. Now, this mass m can be determined as pi r square multiplied by L is the volume multiplied by rho, that is density, is nothing but the mass of this particular the link. So, half m r square is nothing but the moment of inertia about x x. Now, if I see this moment of inertia about y y, so that is nothing but the volume integration y square plus z square dm. So, sorry, x square plus z square dm. So, in place of z square, I am putting r square cos square theta, and next is your dm is rho r d theta dr dx, and if you carry out this particular integration and if these are the limits for integration. So, very easily you can find out. So, this particular expression for I y y, that is nothing but the moment of inertia about y y, that is m L square by 3 plus m r square by 4. So, following this I can also find out the moment of inertia about z z, and that is nothing but volume integration x square plus y square d m, and y square is nothing but r square sin square theta, then rho r d theta d r dx, and if we carry out this particular integration, we will be getting m L square by 3 plus m r square by 4. So, I can find out the moment of inertia about z z. The next is your the product of inertia. The product of inertia I x y is nothing but the volume integration x y d m. Now, here, so y is nothing but your r sin theta and d m is rho r d theta d r dx, and these are the ranges for the integration, and if you carry out this integration, we will be getting I x y is equal to 0. Now, by following the similar method, we can also find out what is I y z, and I y z is nothing but is your the volume integration y z d m, and if you carry out this integration, I will be getting I y z is equals to 0. Similarly, I can also find out the product of inertia, that is I z x, and that is nothing but your z x d m, and if I carry out this particular integration, and we will be able to find out that I z x is equal to 0. Now, here, so we have got this particular product of inertia. Now, volume integration x d m, if we carry out, so I will be getting minus half m L, then integration volume integration y d m will become equal to 0, then volume integration z d m will become equals to 0. Now, the mass center, that is x I bar, y I bar, z I bar is nothing but minus L by 2 0 0. Like if I draw this particular circular cross section, that robotic link. So, my x direction is along this particular direction and the total length is L. So, its mass center will be here, whose coordinate is nothing but minus L by 2 0 0. So, this is nothing but the coordinate of the mass center. Then comes your integration, the volume integration over d m. So, is nothing but m. So, we can find out all such integration, and this is once again the volume integration. Next is your, so once you have got all such expression, now I can find out the inertia tensor. So, this inertia tensor for this particular link with circular cross section, that is denoted by J I, will become equal to m L square by 3 0 0 minus m L by 2, then comes 0 m r square by 4 0 0 0 0 m r square by 4 0 minus m L by 2 0 0 m. Now, if I consider the slender link that where r is very large compared to r, L is very large compared to your r, in that case this m r square by 4. So, this can be neglected. So, this tends to 0, then m r square by 4 tends to 0. So, this will become the inertia tensor will become m L square by 3 0 0 minus m L by 2, then comes 0 0 0 0 0 0 0 0 minus m L by 2 0 0 m. So, this is nothing but your the inertia tensor for the robotic link having circular cross section of radius r. Now, here, so till now we have considered the rectangular cross section having the dimension a and b. So, I can also consider the square cross section like having the dimensions a and a. So, for this particular square cross section robotic link, we can also find out the inertia tensor. Now, if you see in robot, we generally do not consider, so this type of robotic link having the constant cross section. If you see in the robotic link, the cross section is varying. The same is true in our hand also. For example, say if I consider, say this is the robotic links. Now, if I take one cross section here, if I take another cross section here, the cross section is not the same. So, cross section is going to vary and it is having the varying cross section. So, determining this inertia tensor is not so easy. The same is true for the actual robotic link. In actual robotic link, generally we do not consider the link with constant cross section, and the cross section is going to vary along the length. So, it is bit difficult to determine the inertia tensor. In fact, we try to take the help of some sort of finite element analysis to find out what should be that particular your inertia tensor. So, this is the way actually we try to find out the inertia tensor for the robotic link. And once you have got the inertia tensor, now we are in a position to determine the expression, the mathematical expression for the joint torque or the joint force. Now, here actually we are going to use Lagrange-Euler formulation. Truly speaking, this is the Lagrangian method, Lagrange approach. Now, the rule is, or the equation is something like this: d dt of partial derivative of L with respect to q I dot minus the partial derivative of L with respect to q I is nothing but your tau I. Now, I am just going to define the different terms. So, here the t is nothing but time. Now, L is nothing but the Lagrangian, and Lagrangian of a system, of a robotic system, is nothing but the difference between the kinetic energy and the potential energy, that is nothing but the Lagrangian of the robotic system. Now, here this q I is a generalized coordinate. For example, if it is a rotary joint, so q I is nothing but theta I, that is the joint angle. If it is a prismatic joint, that is nothing but the link offset, that is d I. Now, q I dot is nothing but the first time derivative of q I, and your tau I is nothing but the generalized torque if it is a rotary joint, and if it is a linear joint, that is nothing but the generalized force. So, our aim is to determine the mathematical expression for this particular the tau. Now, let us see how to determine the mathematical expression for this particular tau. Now, to find out this mathematical expression, the first thing we will have to do is we will have to find out the expression for this particular the Lagrangian, and this Lagrangian is nothing but, once again this is the difference between the kinetic energy and the potential energy. That means, we will have to determine the kinetic energy for the whole robot, and we will have to find out the potential energy, and this particular difference of kinetic energy and potential energy is nothing but is your Lagrangian. So, my first task is to determine the Lagrangian of this particular the robotic system. Now, let us see how to determine the Lagrangian of this particular the robotic system. Now, let me once again start with a particular the element, small element, whose the coordinate in its own the coordinate system. For example, say if I consider just like the previously the way I consider, say I have got a robotic link, and here the coordinate system I am having here, and your the motor is connected here. Okay. So, I am just trying to find out the mass center here. So, and if I just consider e particular point or say this particular point. So, this point in this coordinate system is nothing but r I with respect to I. Now, with respect to the base coordinate system, so the same point I am just going to find out, and that is nothing but is your r I with respect to 0. So, our aim is to determine, so this particular r I with respect to 0 but this particular point. So, I am just trying to find out. So, this particular point, not this. So, this particular point with respect to your the base coordinate system. So, this is nothing but r I with respect to 0, and this I am trying to find out, provided this is known, that is r I with respect to I. So, this r I with respect to I is nothing but x I, y I, z I 1, and this r I with respect to 0 is nothing but t I with respect to 0 multiplied by r I with respect to I. Now, this t I with respect to 0 is nothing but t 1 with respect to 0, t 2 with respect to 1 up to t I with respect to I minus 1, and this particular t is nothing but the transformation matrix. Once again let me repeat. So, this is actually the circular link and my coordinate system is here. Okay. So, I have got a point here, and with respect to this particular coordinate system. So, this dimension is nothing but r I with respect to I, and I have got the base coordinate system here, okay, and the same point I am trying to find out, and that is nothing but is your r I with respect to 0. So, r I with respect to 0 is nothing but t I with respect to 0 multiplied by this r I with respect to I, and this is nothing but the ith coordinate system, and this is nothing but the base coordinate system. So, in ith coordinate system, so this particular the position vector is known. Now, I am trying to find out r I with respect to the base coordinate point, base coordinate frame, the same point. So, this is the way actually we can represent your r I with respect to 0. Now, actually what I am going to do is, I am trying to find out the kinetic energy of the whole robot. Now, if I want to find out the kinetic energy is nothing but half m v square. So, the expression for the kinetic energy is nothing but half mass multiplied by v square. So, this is nothing but the kinetic energy. Now, here actually what we are going to do, first we are trying to find out the kinetic energy of one small element lying on a particular link. Then we are trying to find out the kinetic energy for the whole link, say ith link, and after that we will try to find out the kinetic energy for the whole robot or the whole robotic system. Now, to determine the kinetic energy of the particle, so what we do is we will have to find out the velocity of the particle. Now, the velocity of the particle, that is v I with respect to 0 with respect to the base coordinate frame. So, this is nothing but the rate of change of the position, that means your d d t of r I with respect to 0. So, this r I with respect to 0 is nothing but the position of that particular the differential mass with respect to the base coordinate frame, and rate of change of that particular position with respect to time is nothing but v I with respect to 0. That means, the velocity of that particular particle with respect to the base coordinate frame. Now, this r I with respect to 0, as I told, can be written as t I with respect to 0 multiplied by r I with respect to I. Now, this t I with respect to 0, so this can be written as t I with respect to 0 is nothing but t 1 with respect to 0 multiplied by t 2 with respect to 1, and the last term will be your t I with respect to I minus 1. T stands for your transformation matrix. Now, I will have to find out the derivative with respect to time. So, this t I with respect to 0 is nothing but this. So, if I find out the derivative with respect to time, so first I will have to concentrate on this, that is t 1 with respect to 0 dot multiplied by t 2 with respect to 1, and there are a few terms, and the last term is t I with respect to I minus 1. The next term will be like t 1 with respect to 0. So, here t 1 with respect to 0, then t 2 with respect to 1, dot, then comes your the last term will be your like T I with respect to I minus 1. Okay. So, multiplied by R I with respect to I, and the last term will be this, that is T 1 with respect to 0, T 2 with respect to 1, and the last term is your T I with respect to I minus 1 dot multiplied by R I with respect to I plus T I with respect to 0. So, this particular R I with respect to I dot. So, this is another term. So, this is the way actually we can find out your this particular the time derivative. Now, let us try to concentrate on this particular term. Now, if we concentrate on this particular term, so this R I with respect to I dot means what? Supposing that I have got one robotic link, the rigid link something like this. Now, if this is the rigid link and I am just going to concentrate on a particular point, okay, and this supposing that I have got the coordinate system here. So, this is actually the position of this particular the differential mass, okay, and this is nothing but R I with respect to I dot. Now, the rate of change of this particular position with respect to time will be 0, because this is a rigid link. So, this is a rigid link. So, for this particular rigid link, your this R I with respect to I dot is nothing but is equal to 0. So, this particular term will become equal to 0. So, we are left with this up to this. Now, here I just want to mention that if we consider robotic link like flexible robotic link, we cannot assume that this R I with respect to I dot is equal to 0. So, this will become non-zero for a flexible ring, and we have a few robot having flexible link also, and determining this particular your V I with respect to 0 is not so easy, and we will have to consider. So, this particular your flexible link and this particular term is non-zero, and to determine once again we will have to take the help of finite element analysis. Now, here actually what we do is, so if you can see, so this particular term can be written like this in a short form. Now, if you concentrate on this, so that is your d dt, that is the derivative with respect to time of your T I with respect to 0. So, this is nothing but the transformation matrix. Now, d dt of T I with respect to 0. So, this can be written as the partial derivative with respect to your q j, partial derivative with respect to q j multiplied by d q dt. So, d dt of T I with respect to 0 is nothing but the partial derivative of this of T I with respect to 0 multiplied by d q dt. Let me write it once again. So, d dt of T I with respect to 0 is nothing but the partial derivative with respect to q j of T I with respect to 0 multiplied by is your d q dt. So, it can be written something like this. Okay. So, this particular term has been written in this particular form, that is your partial derivative with respect to q j of T I with respect to 0, and d q dt is nothing but q j dot. Okay. And we have got this particular thing, that is R I with respect to I. So, this particular expression can be written in short form like this, and this is nothing but is your like V I with respect to 0. That means, your the velocity of that particular particle with respect to the base coordinate frame is nothing but, so this particular the expression. Now, here I am just going to use another symbol, that is partial derivative of T I with respect to 0 with respect to your q j is nothing but u I j is another symbol I am using. That means, your V I with respect to 0 can be written as summation j equals to 1 to I, then comes u I j. So, u I j is what? So, this in place of this particular, so I am using u I j multiplied by q j dot multiplied by r I with respect to I, and here this u I j k is nothing but the partial derivative of u I j with respect to q k. So, these particular symbols we are going to write down just to write in a very compact form. So, let us see how to write down this particular thing in a very compact form. Now, kinetic energy of the particle having the differential mass is nothing but half m v square. Now, here the mass of this particular differential mass is d m. So, half d m v square. Now, here this particular velocity, which is a vector, has got 3 components. So, this particular components velocity has got your 3 components like say x I dot, then comes your y I dot and z I dot. So, these are the 3 components of this particular the velocity. Okay. Now, here, so this the kinetic energy of the differential mass d m, the small particle, that is d k I is nothing but half d m, then x I dot square plus y I dot square plus z I dot square. Now, this v bar, that is nothing but v I with respect to 0 is nothing but this. Okay. And now, this v I with respect to 0, trace of that. So, this is nothing but a 3 cross 1 matrix, and I can write down actually here like its trace is nothing but x I dot y I dot, then comes your z I dot. Okay. Now, here if I just multiply, so I will be getting your first row first column, that is x I dot square, x I dot square, then first row second column x I dot y I dot, then comes your z I dot x I dot, then y x. So, I will be getting x I dot y I dot, then comes your y I dot square, then comes your y I dot z I dot, then comes your z x, that is z I dot x I dot, then comes your y I dot z I dot, and then comes your z I dot square. So, this type of like 3 cross 3 matrix we will be getting. Now, here we try to concentrate only on the diagonal elements, and these diagonal elements is nothing but trace of this particular the matrix. Okay. So, x I dot square plus y I dot square plus z I dot square, and that is actually nothing but trace of. So, trace of, so this particular v I with respect to 0, v I with respect to 0 transpose. So, trace of that is nothing but x I dot square plus y I dot square plus z I dot square d m. Now, this d k I is nothing but your half trace of this v I with respect to 0. Now, we have already derived that v I with respect to 0 is nothing but summation a equals to 1 to I u I a q a dot r I with respect to I. This I have already seen, and then your, so this particular v I with respect to 0 t prime, this is nothing but is your summation b equals to 1 to I u I b q b dot r I with respect to I, trace of that d m. Now, here one thing I just want to mention. Now, here this summation I have taken a equals to 1 to I, and here I have taken b equals to 1 to I, and this I have done very purposefully. For example, say if I consider, so it is a rotary joint. So, in place of this q a dot, I am just going to write down theta a dot, and in place of this q b dot I am just going to write down like q b dot. Now, if you see the final expression which I am going to derive, so there is a possibility there will be a few terms like theta 1 dot multiplied by theta 2 dot, then might be theta 2 dot multiplied by theta 3 dot, something like this. Okay. Now, if I do not consider the separate range for this particular summation, so I am just going to miss this particular the combination of theta 1 dot multiplied by theta 2 dot. Now, if I consider both are a equals to 1 to I and b equals to 1 to I, so there is a possibility I will be getting theta 1 dot square. Now, for a very special case I will be getting theta 1 dot square and where a will become equals to b, but just to keep this particular possibility alive. So, I have taken two separate range for this particular the summation. Now, once I have written like this, we can rearrange in this particular format half trace summation a equals to 1 to I, summation b equals to 1 to I, u I a, r I with respect to I, r I with respect to I transpose, then comes u I b transpose, then q your a dot q b dot d m. This can be further rearranged in this particular format half trace summation a equals to 1 to I, summation b equals to 1 to I, q I a, then this r I with respect to I d m, r I with respect to I transpose of that, then u I b transpose q a dot q b dot. So, it can be rearranged in this particular the format. Thank you.